Hello everyone. Let's analyze. So there have been many ways that we might consider, express, describe, parameterize a circle in the plane. One way is to define the function f of x and y as x squared plus y squared minus 2. Then the set of every ordered pair x, y that satisfies f of x, y is equal to 0 forms a circle of a radius square root of 2. We see an example there to the right. But can we say that the equation f of x comma y equals 0 implicitly defines a function y equals f of x? Well, if we look at the picture, every x and y satisfying f of x, y equals 0 forms a circle. And of course, we know the circle fails the vertical line test. However, what about for portions of the circle? So is there a function y equals f of x for which f, x, and f of x is equal to 0? Well, in other words, can we take this expression here, solve for y as a function of x, and then insert it back into here? All right, well, of course, for the circle, there are two such functions. There's the square root of 2 minus x squared and negative square root of 2 minus x squared. We'll call them f plus and f minus. But neither is exhaustive. Neither captures the set of all ordered pairs, satisfying f of x and y is equal to 0. So then we might ask, for a particular ordered pair x naught and y naught, satisfying f of x naught and y naught is equal to 0. In other words, they're on the circle, right? So for 2 points on the circle, is there a function y equals f of x that passes through it? In other words, y naught equals f of x naught, f of x comma f of x naught equal f of x equals to 0, for which the function little f is continuous and unique in a neighborhood of x naught. Well, for the circle, we can do that unless x naught is at plus or minus the square root of 2. In other words, those left and rightmost points in the circle marked in red to your right. Well, what went wrong there? Why can't we answer this question in the affirmative if x naught is plus or minus the square root of 2? Well, both f plus and f minus capture the ordered pair or pass through that ordered pair, square root of 2 comma 0 or minus square root of 2 comma 0. So certainly there's no unique function that captures it. Furthermore, the function f, right, we would like for it to be continuous and even differentiable, but neither is differentiable at those red points because the tangent line at those points is vertical, which is to say the change of f, big F, with respect to y at that point is 0. In other words, the rate of change in the y or vertical direction is 0. So that's what went wrong. So another application where we might want to define y as a function of x implicitly is in solving the following initial value problem. You might vaguely recollect from your days in ordinary differential equations that that is a separable differential equation in the top row. So the solution is defined implicitly. It's every x and y pair satisfying that this expression is equal to 0. But is there a unique function y of x satisfying that this expression, which we're going to name big F, is equal to 0 near my initial condition? Well, note that if I take the derivative of this expression with respect to y and evaluate at my initial value, I get n of y naught. So if the last example is any indication, we don't want n of y naught to be 0. So let's discuss a theorem that would essentially tell us what it looks like if f does define an implicit function. In this theorem we call g of x. So suppose f maps an ordered pair from Rm and Rn to Rn. Now, by the way, we're thinking of f as a function of an ordered pair, let's say x and y. X is in Rm and y is in Rn. Why not just let f be a function of z, where z is length m plus n? Well, because we want to distinguish the m-dimensional part and the n-dimensional part, because the idea is to implicitly define a function from Rm to Rn. Okay, so suppose f, big F, is C1, and there's an open subset of Rm and an open subset of Rn, for which their cross product, or the set of all ordered pairs from V and W, is contained in the open domain of F. And suppose that there is an implicitly defined function g, mapping V to W. That's C1. When I say there's an implicitly defined function, what I mean is x and g of x satisfy the equation f of x comma y equals 0, right, where y is taken by g of x. And it satisfies the equation for all x in this open set V of Rm. So that's our hypothesis. In other words, if we're in a setting where an implicitly function is implicitly defined, then for all x and v, since everything is C1, we can take a derivative, and the derivative of f with respect to the first argument. Right, remember, we can think of f as a function of a single vector of size Rm plus n, but because we're separating it, when we take the derivative, we have to say we're taking a derivative with respect to that first argument or the second, right? Of course, the total derivative would be with respect to both. So the derivative of f with respect to the first argument, evaluated at x and g, plus the derivative of f with respect to the second argument, again evaluated at x and g, times the derivative of g is 0. In particular, if this matrix is invertible, then we can solve for this derivative matrix. And it's given by subtracting this term to the right and multiplying by the inverse of this matrix, which is guaranteed if its determinant is non-zero. So let's work our way through the proof. Let H map V to V by W. Right? Remember, V is the set from which the first entry of an ordered pair is taken, and it's going to map V to an ordered pair, V by W. Right, the idea is that G is going to map V to W. So I get an ordered pair in V and in W. And so we say H of x is x comma G of x. Then f of x comma G of x, remember, G is implicitly defined by the equation f of x y equals 0. So f of x comma g of x is 0 by assumption, and I'm saying that this argument of f is what I've defined h to be. So this is equal to the composition of f and little h, and again by assumption that's 0. And if it's 0, then, well, the derivative is 0. Of course, because now I'm thinking of f as a composition of f and h, I can use the chain rule to give me more detail about this structure. From the chain rule, we know that the derivative of f composed at h at x is the derivative of f at h of x times the derivative of h of x. So the derivative of f will leave in blue, and the derivative of h, defined here, will leave in red, so that we can track how these different parts combine and move about as we go forward. So what is h of x? Well, h of x is by definition x comma g of x. What is the derivative of h? Well, the derivative of the first entry of h is just the identity, and the derivative of the second entry is just the derivative of g. So we get this. Right here, I'm thinking of h as a mapping to a vector in Rn plus m. So I have to take the derivative with respect to all the entries, which means all of these entries and then all of these entries, which is why I get this. Now, what is the derivative of f? Remember, this is a total derivative. So here I'm taking a total derivative of all the arguments of f, of which there are n plus m of them. Well, it means that I take the derivative of f with respect to the first argument and with respect to the second argument of f. So I get what looks like a block, almost kind of a multidimensional gradient transpose. Right? I get the derivative of f with respect to the first entries, and then the derivative of f with respect to the second entries. That means I can take this term and expand it into this and this term. And after I multiply this block 1 by 2 times this block 2 by 1, I get exactly this. So again, the derivative of f at h, right, we're keeping in blue, and the derivative of h at x we're keeping in red, so you can track how they mingle. Well, it follows that, remember that the derivative of this is 0, so this is equal to 0, which is exactly what we see here. That red identity matrix went away because, well, it's the identity matrix, like multiplying by 1. And this is true for all x and v. That is, all x in the domain of h, which is to say all x in the domain of g. So if, in addition, this matrix is invertible, then I can solve for dg. Right, as I stated before. So we've proven our result. So now we're ready for the implicit function theorem. So first, let's discuss the hypothesis. Suppose f maps ordered pairs of vectors in Rm and a vector in Rn to Rn, where the domain of f is open, it's class C1, and the particular ordered pair AB is in the domain of f, and f of a comma b is equal to 0, and the derivative with respect to the second argument of f is invertible. In other words, its determinant is non-zero. So if this is true, then there are open and connected subsets V and W and a unique class C1 function G that maps V to W, right? V in Rm to W in Rn, such that the ordered pair AB is in the set of all ordered pairs from V and from W, which is contained in the domain of f, G passes through that ordered pair. In other words, G of A equals B. And furthermore, G is implicitly defined by F. In other words, F of X and Y set to G of X is 0 for all X in V. And in particular, we can compute the derivative of G using the evaluation of the derivatives of F with respect to X and Y at our ordered pair A and B. Now, by the way, the third component, or this last in particular part, is implied from the previous theorem. So we won't prove that because, again, once the above is true, then we have exactly the setting of the previous theorem. So before we get into proving the implicit function theorem, let's work out an example just so that we can see and visualize exactly what this problem looks like. So suppose F maps a two-dimensional vector x and a two-dimensional vector y to a two-dimensional vector. So for example, we have f of x comma y equals x1 squared plus x2 squared minus 2x1 times y1 times y2. The second entry of f is 3x1 x2 minus 2y1 squared minus y2 squared. So again, I could just think of f of z, where z is the four-dimensional vector x1, x2, y1, y2. But again, the idea is that if I take all ordered pairs x and y such that f of xy is equal to 0, does it implicitly define a function? For the reasons we stated at the beginning, right? Lots of times we implicitly define functions, but we want to make sure that they really are functions. So, does f satisfy the hypothesis of the implicit function theorem? Well, notice that if the vector A and the vector B are both the 1, 1 vector, then f of A comma B is equal to 0. Right, if I plug in x1, x2, y1, y2 all equal to 1, then I get f at those points is 0. And f is class C1. So the derivative of f, and again here I'm just thinking of f as a function of all the entries of x and y, so I'm taking a total derivative. So in that case we would think of f mapping R4 to R2, so the derivative is 2 by 4. But this first 2 by 2 block is the derivative of f with respect to x, and the second 2 by 2 block is the derivative of f with respect to y. If I think of these as separate variables, right, holding one constant, taking the derivative with respect to the other. Okay. Now, if I evaluate at x is equal to a and y is equal to b, and remember both a and b are the 1, 1 vector, I get this matrix. Now, remember, the first 2 by 2 block, that's the derivative of f with respect to x. And I'm evaluating it at a, b. And the second 2 by 2 block is the derivative of f with respect to y. Again, I'm evaluating at a, b. Now, this is the one that we want to be, invertible, right? So let's compute the determinant to make sure it's non-zero. Right, I get negative 2 times negative 2 minus 8 gives me negative 4. Negative 4 is not 0. Okay, so the hypothesis of the implicit function theorem is satisfied. Well, what does that buy us? Well, we know there's an open subset of R2 and an open subset of also R2, where A is contained in that first open subset V and B is contained in the second open subset W. And there is a unique continuous and continuously differentiable function G that maps V to W and that passes through the coordinate AB. In other words, G of A equals B. Right? Furthermore, we can say G is implicitly defined by the equation f of xy equals 0. In other words, y equals g of x satisfies f of xy is equal to 0. for all x in some domain V, this open set V. What is G? I don't know. I mean, perhaps you can figure it out, but I can tell you what the derivative of G is at A. Right? It's given by the equation we discussed, which means it just requires a little bit of linear algebra to get that the derivative of G at A is this matrix here. In particular, the derivative of G at A is, right, a matrix of partial derivatives. So in fact, not only can I tell you what the complete derivative of G is, I can actually tell you what all the partial derivatives of G are at 1, 1. And all of that comes directly from the implicit function theorem. Okay, so you might want to pause here and take some time to review this exercise, this example, so that we understand the setting we're in as we prove the implicit function theorem. Okay, now back to our regularly scheduled proof of the implicit function theorem. Proof. So let H map U to Rm by Rn. Remember, U is the domain of F, right? Big F, which is in the hypothesis of our implicit function theorem. So U is an open set of ordered pairs of vectors Rm and Rn. So in other words, H maps ordered pairs to ordered pairs. And we're going to define H as H of xy equals x f of xy. So notice that H of x, the first kind of ordered pair of H of xy is x. So H doesn't do anything to the first argument. Okay? So that's important. H does nothing to the first argument, but it does something to the second argument and maps it to, well, f of xy. Right? Of course, we're interested in xy for which f of xy is 0. So eventually, we're going to be curious about what h of x0 is. Well, notice that h of ab equals a comma f of ab, and f of ab by hypothesis, right, by assumption of the theorem is 0. So we know that h maps the ordered pair ab, which my implicitly defined function must pass through, right? H maps it to a0, right? Again, h doesn't do anything to the first argument. Now the derivative of h at xy, right? Again, now I'm thinking of the complete derivative. Well, the derivative of this first entry with respect to x is the identity, and the derivative of the first entry with respect to y is 0. The derivative of the second entry of h with respect to x is, well, the derivative of f with respect to h. I mean with respect to x, because that is the second entry of h. And the derivative of the second entry of h with respect to y is, well, the derivative of the second entry f with respect to y. Now, is this matrix invertible? In fact, when we're taking the determinant of a block matrix, we can actually do block arithmetic. I actually get the determinant of this 1, 1 block times the determinant of the 2, 2 block. The determinant of the identity is 1, so I just get the determinant of the derivative of f with respect to y evaluated at ab, which by assumption of the implicit function theorem is non-zero, right? That's one of the things we assumed in order to get into the setting of the theorem. So h satisfies the hypothesis of the inverse mapping theorem, right? Because f satisfies the hypothesis of the implicit function theorem, h satisfies the hypothesis of the inverse mapping theorem, right? H maps ordered pairs to ordered pairs of the same size. It's invertible at a point. The derivative is invertible at a point. So H satisfies the inverse mapping theorem. What does that buy us? Well, there's an open set T containing, right, the image of H at AB, in other words, H of AB. And there's an open set S containing, right, where the derivative is invertible at AB, such that H of S equals T. And H has a C1 inverse that maps T back to S. Right, that's exactly the statement of the inverse mapping theorem. Now, within S, remember S is the domain of H for which H is invertible. Of course, who knows what the shape of S is, right? So, but within S, by the definition of open, right, remember S is a set of ordered pairs. The fact that it's open means I can perturb the first entry of the ordered pair and the second entry of the ordered pair by some amount and still remain in the set. That's what it means to be open. So within S is an open, connected, quote-unquote, rectangle. It's in quotes because, right, V is m-dimensional and W is n-dimensional, so it's not exactly a 2x2 rectangle. But, right, I'm considering some open connected set V by open connected set W. And that's contained in S. Right? Because again, eventually I want to find a function that maps V to W. So because the set of all ordered pairs from V and from W is contained in S, for which H is invertible, you see here, then H of this subset of S is contained in H of S, which is H of T. And of course the inverse of H, which is guaranteed to exist on S, of which this is a subset of, takes it back, right? It takes H of V by W back to V by W. Now, remember the definition of H, right? I'm just repeating what we defined H as. I'm just repeating it down here so we have it right in front of us. Right? H of xy is defined to be x f of xy. In other words, remember, H takes x and does, well, nothing to it. So we know how to invert that part. Right? So if I take the inverse of both sides, I get xy equals H inverse of x, comma, f of xy. So what does H inverse do to x? Again, it just takes it back to x, because H takes x to x. Now, what if I want to evaluate H inverse at some xy? Right, I have instructions for evaluating H at xy, and I know what the outcome of H inverse is. But if I want to evaluate H inverse at some xy, right, which is contained in, right, well, the domain of H inverse, which is the image of H of V by W. Right, so if I want to evaluate H inverse at some point, well, the x gets taken to x, but the y, well, it gets taken to some function of x and y. Right, x gets left alone, but the y argument does not. And the y argument is not going to depend just on y, but rather on x and y. And again, because x and y is in the image of V by W, H inverse is going to map it back to V by W. And this little h function has to be C1 because big H is C1. If H were not C1, if it were less continuous than that, then neither would big H be, by chain rule. So what is the domain of little h? Well, it's the same xy, which is in the image of H applied to V by W. So H maps the image of V by W under H to W, right? Because it maps it to the second entry. It maps it to W, right? Because this ordered pair is contained in V by W. X is in V, H of X comma Y is in W. Okay, so let's say that G maps V, right? The open set where X lives, to W. And we're going to define G of X to be H of X comma 0. Then H inverse of X 0, right? Again, we can just use this formula for H inverse, equals, right? Again, the X gets mapped to X. The 0 is going to get mapped to, well, some function of X and 0. And H of X 0 is what I've renamed to be just G of X. Well, that implies that if I take this expression and apply H to it, H of H inverse of X0 is, well, H applied to this. Well, what's the definition of H? Remember what H is defined as. H is defined as this, so I would get X comma F of X comma H X comma 0. That's just the definition of what I define H to be. And, well, remember that this term here is G. So now let's look at the left and right ends of my expression. I have an ordered pair and an ordered pair. The first entry of the ordered pair X, X, they're equal. Okay, good. The second entry has to be equal if the ordered pair is equal. So 0 equals F of X comma GX. In other words, F of XY equals 0 implicitly defines G for all X in some open set V. So let's repeat that. For all X in V, G satisfies F of X comma Y equals G of X is equal to 0. Are we done? We showed that F of X comma Y equals 0 implicitly defines a function G. Well, does G of A equal B? Is G from the map from V to W, is it uniquely defined? Right, that's also part of the result of the theorem. Well, what's H of AB? H of AB is, of course, by definition, A F of AB, and F of AB we know is 0. Okay. Now, again, if I apply H inverse to this, I get the ordered pair AB equals H inverse of A comma F of AB. But again, remember, F of AB is 0. And what is H inverse of A comma 0? Well, it's A and some, write that function H of A0. Remember, H of A0 is exactly the definition of G of A. So again, I have the ordered pair AB equals the ordered pair A, G of A. The first entry A equals A, the second entry B equals G of A. So, does G of A equal B? Yes. Yes, it does. Now, is G uniquely defined? Well, remember, H inverse of X0 equals X comma G of X. And H of X comma G of X is, by definition, X comma F of X comma G of X. Remember, we show that that is 0. But both H and H inverse are one-to-one mappings. I mean, if they weren't, H wouldn't be invertible. So they're one-to-one mappings. So we're assured of the uniqueness of G by the inverse function theorem. Okay, now we're done. We get our square. So let's discuss a few consequences of the implicit function theorem. If f maps u and Rn to R has a non-zero derivative at x naught, then the domain can be straightened out. Okay, what do I mean by that? In the sense that f can be composed with a smoothly invertible function h, so that f of h of x is just the projection of x onto the nth coordinate axis. In other words, f of h of x is xn. Well, why is this relevant? Well, it's a useful tool in the study of surfaces, right? Because I can define a surface in Rn as all x such that f of x is equal to 0. Well, what this idea of straightening out the domain means is I can take my domain x, right, apply a smooth, differentiable, invertible h to my domain so that when I apply f to it, I just get a projection. So let's give the precise statement of the theorem. Again, hypothesis first. Let f map an open set in Rn to R be Cp, where p is greater than or equal to 1. In other words, at the very least, f is differentiable and the derivative is continuous. Suppose f of x naught equals 0. In other words, x naught is on whatever kind of surface we're defining, and the derivative at that point is not 0. Of course, remember that the derivative of such an f was just a gradient transpose. Okay, so what does that buy us? Then there's an open set W and V containing x naught, both in Rn, right? So W and V are both in Rn, and a class Cp function h that maps W to V, right? This is what's going to straighten out our domain for us. It's what's going to warp our domain, but in a differentiable and invertible way. Right, so h has a class Cp inverse, right? So that f of h of x, right, is essentially just a projection, It's equal to xn, the projection onto the last coordinate axis. Okay, so let's give a sketch of this proof, just so we have an idea of the different ways that the implicit function theorem is applied to glean other results, in this case about surfaces. So of course this result might be useful if you were to go on and really study in depth surfaces in higher dimensions. If you do, I hope you would look back upon this video and perhaps refresh some of your understanding. So the derivative of f, which is the gradient transpose, is not 0, which means one of the entries of that vector is not 0. And that vector is, well, an array of partial derivatives. So one of those partial derivatives is not 0. Let G be the permutation function that just swaps the ith and nth entry of x. So that's all G does. It takes the ith entry for where the partial derivative is not 0 and the last entry and just swaps them. Then if I take the nth partial derivative of f composed with G, right? In other words, that means whatever entry was at I is going to get moved to n, and then it's going to get moved back. Okay, remember that G is its own inverse, right? If I swap the ith and nth entry and then swap them again, I get back to where I started from. So if I take the ith entry, swap it to the nth entry, take a derivative, right? I know it's not 0 at the ith entry, and then swap it back, then I just get the ith derivative. I just get the ith derivative, which we know is not 0. That implies that the composition function, f with g, now notice how we're defining it. We're not saying f of g of x. We could, but we're actually going to split x into the first n minus 1 parts and the last entry. So this composition satisfies the implicit function theorem, right? In the implicit function theorem, this is our x and this is our y. And the derivative at y we saw is non-zero at, specifically at g of x naught. So this x1 colon n minus 1, right? That's just the first n minus 1 entries of x. So this composition satisfies the implicit function theorem. As in the proof of that theorem, let h of x, right? We're going to split x in the same way. The first n minus 1 entries and the last entry. The first n minus 1 entries get left alone, right? And then the last entry is f composed of g of x. Then, just as in the proof of that theorem, h is also invertible on some open set containing x naught. And the image of h on this open set contains the point x naught comma 0. That's because I can take one of the outputs of f is 0 because f of x naught is 0. So if g of some value equals x naught, I get 0 here in this last entry. Therefore, xn, which xn is just the inner product of en, which is a vector of all zeros except for a 1 in the last entry, with x. That's my projection. xn equals the projection. Well, x is h of h inverse of x. That's what it means to be an inverse. Now, h inverse of x is some vector. What is h of that? Well, h of some argument is, right, it leaves all first n minus 1 entries alone, and it does this to the last entry. And en transpose, right, en transpose has the function of extracting the last entry. So en transpose of h is just f composed g of x with h inverse of x, which is how I get this expression, right? Because en transpose extracts the last entry of what h does. And the last entry of what h does is that. So I can just rewrite this composition as f of g of h inverse of x. Well, remember where I started from. That's xn. So that's essentially my result. If I let h be the composition of g and h inverse. Okay, so that's a sketch of how you might apply the implicit function theorem to show this result. Of course, the continuity class of h and its inverse, it follows from the inverse function theorem. So if we can construct a smoothly invertible h such that f composed with h is a projection, can we construct g such that g composed with f, in other words, g is going to accept the output of f, that is the range of f. Can we construct this g so that g composed with f is a projection when the range of f is in multiple dimensions? Yes, it's known as the range straightening theorem. If f maps an open subset of Rm to Rn is class Cp, and the rank of the derivative at x naught is m, right, the dimension of the range, for some x naught in the domain, then there's an open set V and W which again is going to map the output of f of x naught, right, to w. And there's a g, my range straightener, okay, that's going to take the output of f to w, which is again still in the same setting of the codomain of f, Rn. G is also going to be class CP and have a class CP inverse. And on some neighborhood of x naught, G composed with f will be a projection of x onto the first m axes. In other words, I'll get x1 through xm, and then all the other entries will be 0. So we won't prove the theorem, but the proof is in the book if you want to read it. The rank theorem. Suppose f maps an open Rn, an open set in Rn to Rk. Suppose it's class CP and the derivative has rank m. Then for all x in some open neighborhood of x naught within the domain of f, then there's open sets u and v in Rn. V contains x naught. There's a function h from u to v of class CP with the class CP inverse, such that f composed of h depends only on the first m entries. Okay. In other words, even though f accepts vectors in Rn, because its derivative is rank m, right, where m is necessarily less than or equal to n, because it's rank m, right, we can construct a kind of a warping of the domain so that f really only depends on the first m entries, and we retain the smoothness of whatever f originally was. So again, these last three theorems, the domain straightening theorem, the range straightening theorem, the rank theorem, these are really useful in understanding how surfaces and higher dimensions can be warped and distorted in smoothly differentiable, well, that's redundant, but also in invertible ways, which, right, you may come across in your future if you were decided to really study this field or have applications in the work that you're doing. Well, that's it for today.